So let's do this. All right, so we're going to talk about exponential growth and decay. Basically, this lesson is about the applications in real life of exponential functions. First thing we're going to talk about is compound interest. All right, so when we're talking about compound interest, it has to be in reference to a bank account, right? So this is when you have money in a bank account and it's gaining interest. Now, depending on the type of bank account, the bank might pay you interest just once a year, or twice a year, or 3 times a year, and so on. So that's what we have to calculate here. The formula is this: A equals P 1 plus R over N to the NT. All right, now let's talk about the variables used in the formula. All right, so A is the final balance in the account, meaning, like when you get your statement, how much is there now? Or at the end of 10 years, how much is there in the bank account? P is the principal, not Miss Howard. It's the money that you go to the bank with to open up your account, okay? Rate, R is rate in decimal form. So basically, whatever the rate is, you have to divide it by 100. I have to say, in my 17, 18, whatever years of teaching, the most common mistake in these problems is students don't divide. So if the rate is 5%, they put in 5, and then you get the wrong numbers. T is the time in years. That's self-explanatory. Okay, N. That's the little n in the exponent. N is the number of times within a year that the customer is paid by the bank. And that depends on the type of account you have. So, if in the problem you're told that interest is paid annually, how many times a year is that? Once. So N is equal to 1. Semi-annually, what is N? 2. Quarterly? 4. Monthly? 12. Daily? 365. How many times a year? How many times a year?
Once a day.
Okay, so 365 a year. And we're not going to deal with leap year, okay? There's no leap year in math. Okay. So, here we go. Problem 1. Mrs. Algebra invested $2,000 into an educational account for her son when he was an infant. The account has a 5% interest rate. If Mrs. Algebra does not make any other deposits or withdrawals, what will the account balance be after 18 years if the interest is compounded as follows? So now we have 3 parts to this problem, A, B, and C. Right, so now let's talk about 2,000 is the principal. So P is 2,000. What is the 5%? That's the R, and it'll be 0.05. What's 18 then? Right, T is equal to 18. And what's N for quarterly? 4. Now, if you would like full credit on homework and tests and quizzes, I would like to see you write down all of this information, okay? The next step is write down the formula. P 1 plus R over N to the NT. Now let's plug them in. A equals 2,000, 1 plus R over 4 times 18. All right, So let's go on our calculators and I'll show you how to put this in. I would like you to be able to put all this information in one shot. So it's 2,000 parentheses, and you just put it in the way you see it. Okay? When you do this, it just divides 0.05 by 4 to the power of 4 times 18. So the amount is 4,891 point what? Just 8.84. This is dollars and cents. So please, I shouldn't have to tell you to round to 2 decimal places. It's money. Cents go to the hundreds place. Huh?
No, it's 18, but
It's 18, but you couldn't see it. It cut off. Like,
oh, okay, sorry.
yeah. Depending on your calculator, you might need to input differently. Now, furthermore, you have to be dead on when it comes to rounding. So if it's like 8.4 versus 8.5, it's going to make a huge difference. This is money. Imagine if it was okay for these banks to make mistakes, like even by a penny. If they were off by a penny on every single account, the world would collapse. Like everything would be wrong. Okay? All right. So the next one is monthly. And if you have a situation like this, here's how I want you to show the work. This information, you could just write it one time because it's going to repeat. Here, I say, okay, n is equal to 12. So A is P, 1 plus R over N to the NT, 2,000, 1 plus 0.05 over 12, 12 times 18. Okay, now. So look at what I do. Please don't type everything over again. Here's what I do. Second, enter. It gives back the last equation you put in. Now I just go in and modify. So this is going to be 12. And I'll show you how to insert. Look. You come here, right? I put in a 1. Now there is no space for the 2. When you do second, delete, or insert, you can put in any other number, like it inserts a number like word. Enter. 4,910 and 0, how much? 2. Right, so now, in the first case, the bank was paying them 4 times a year. Now, they're paying them every month, so, she's getting more money. Okay, so what if she's getting paid daily? N is equal to 365. She's going to break the bank with this one. So, P, 1 plus R over N to the NT. So it's equal to 365 times 18. Second, enter. Here. 3, 6, insert 5. 3, 6, insert 5. Okay. So we get so much more money. $8 more to be exact. Over the 18 years. Right? So these are how much she's going to have at the end of 18 years. So this much if it's quarterly, 4,910 if it's monthly, 4,918 if it's daily. Point being, you're not going to make millions off of this, okay? Now, so what if you're just like, okay, you know what? Like, this is not enough. I need to make more money. Can't you pay me more than 365 times a year? And the representative at the bank goes, okay, how about if we pay you every nanosecond of every minute of every day? That's like, we're paying you continuously. So if it was every nanosecond of every minute of every day, how many times a year is that? Infinite amount, right? It's an infinitely large amount. So every second. So in that situation, the formula then changes. That's an actual thing. So now we have continuous interest. Continuous. It's the APERT formula. You use it only when interest is compounded continuously. So, same situation. P is 2,000. It's the same Mrs. Algebra. R is 0.05. Now, look, you see the key word here, continuously. We're going to use A equals PE to the RT, right? And T is 18. She is going to make so much money. E to the 0.05 times 18. Let's plug it in. 2,000 E to the 0.05 times 18. Okay, drum roll. Whoa, a whole dollar more. Yep. Why? You know why? Because of the way the formula is made. Here, in the other one, we had P 1 plus R over N to the power of NT. This, as N gets infinitely large, it levels off to 2.718, blah, blah, blah. What number is that? E. That's how we can take that out and put in an E. So it caps off after a while. It levels off. Isn't that cool? Math is so cool. Okay. So these two formulas, you use them only for bank accounts. All right? Because the letters in there, P for principal and so on, these are specifically for bank accounts. Now, but that's not all exponential functions are used for. In addition to investments, we use this stuff for populations of people, animals, bacteria, radioactive decay, okay? All of this stuff change at an exponential rate. So, here are the formulas for exponential growth and decay. And I made this chart specifically for you guys. So, exponential growth or decay, this is the formula. This is actually like the original formula. Okay, like this is the OG formula. Everything else is a derivative of this. Here's what you need to watch out for. If the specified quantity is increasing, population is increasing, bacteria is increasing, then use positive R. If the specified quantity is decreasing, there's a population of foxes that are dying, there is some radioactive material that's decaying, you use negative R. Okay, when do you use this formula? You use this formula for problems that involve quantities which increase once a year only. On a specific calendar day, it increases. For example, your rent. Like every June 1st, it increases. Salary, every January 1st, you get a raise. Okay? Things like that. The value of your property, would that qualify here? Let's think about that. If you bought property, and let's say it increases like 12% a year. So let's say you bought the property on September 1st. So what happens, like that entire year, it's the same amount, and then on September 1st, all of a sudden it's more? No. So what if like you're 2 months in? It still accrues value. So something like that you wouldn't use this for. Okay? You see what I mean? Like the value of a car decreases after you buy it, right? Every year. Let's say, whatever, 3%, 5%, whatever, okay? So let's say you bought a car on September 1st, 2017. 5 months after that, does it have the same value or less? Less. Because it actually starts losing value the minute you drive it off, right? Correct. So that's a continuous change. It's not like, okay, same amount, same amount, same amount. Okay, September 1st, now it lost value. No. For those, we use continuous growth or decay. And this is the formula for that. Here, K is rate, not R, because it was too simple to have the same variable. If the quantity is increasing, positive K, decreasing, negative K, you use this for problems involving quantities which increase continuously or decrease. For example, population, radioactive decay, half-life, and then we can add to this like property value, and so on. Okay? All right. Variables used. N is the final amount. N naught, this is one efficient thing mathematicians and scientists do. Rather than using two different variables, A and P, we say N and N naught. The little subscript 0 is read as naught. So N naught is the original, initial. It's like NOT. It's like, you know, in physics, it's like VF, VI. Yes. This is N and N naught. So instead of having VF and VI, we would have like V and V naught. Okay? Or N and N naught. Huh? The 0. So R or K is the rate. Time is T, and it's usually in years. Okay. All right, so a state's population is declining at a rate of 2.6% annually. Okay? They closed like Disneyland and everybody's moving out of California, whatever. So the state, so here's one piece of information. Right. Right, so 2.6% annually. Well, this for now is the rate. Okay? Or, right. The state currently has a population of approximately 11 million people. That's initial. If the population continues to decline, predict the population in 15 years. So, first of all, let's figure out what formula we're going to use. The population is decreasing 2.6% annually. So let's think about this. Is it like people are leaving throughout the year? Or is it like every single like August 15, 2.6% of the population packs up and leaves? It's not like that, right? So it's continuously. So it's N equals N naught e to the KT. So let's figure out what we have here. N is what we need. N naught is 11 million. K is 0.001. 0.026 T 15. So N equals, don't put 11 million, just put 11, and then remember your answer is going to be in millions. E to the 0.026 times 15. So, Gabby, are you on this?
Oh, okay. 16 million.
Yeah, so the population is decreasing. We're going to have fewer people. Oh my gosh, you do.
Good job, Aaron.
I'm giving you a participation point. Okay? So negative. Way to go. So, do we have to plug in 11 million? No. And then just remember that it's going to be millions. So it's 7.45. So does that mean there are 7.45 people left? Million. So let's do this. N is 7.45. So 7.45 million. And now, that symbol, what does that mean? Approximately. Good. So go ahead and do the one for 30 years, and I'll stop this and we'll come back in 2 minutes. When we look at the 30 years, we're going to have about 5.04 million people. Okay? Fabulous. Questions? Okay. Moving on.